Let us continue with our 25th lecture on the process control course. We have been talking about Nyquist stability criterion and how we understand stability of time delay systems. We started doing this because the things that we have learned in terms of partial fractions and a Bode-Ruth stability table were not useful anymore. So, we said we now have a situation where I have a transfer function which is a numerator by denominator transfer function, and the denominator has this exponential term. So, I get a polynomial of infinite order. So, both the partial fraction idea and Ruth stability table are not going to be useful anymore. So, we were looking at other ways of doing this, and in the last lecture I talked about how you think about these transfer functions and the poles and zeros of the transfer function. The reason why we are interested in the poles and zeros of the transfer function is because the poles really tell you the stability of the system. So, what we are trying to do is we are trying to find out if there is some way in which I can figure out if there are poles of this transfer function in the right of plane for systems with time delay elements, particularly in the denominator polynomial. So, that is the reason why we are looking at f of s and looking at poles and zeros of f of s. While all these results are going to be applicable for time delay systems, at the beginning to explain the ideas, we said we will still look at numerator by denominator polynomial, which can be written as root resolve forms with zeros in the numerator and the poles in the denominator. So, we are going to look at those kinds of systems. We are going to show you the main result of Nyquist stability and then connect that to control systems, particularly closed loop transfer function. And then finally, we are going to say these results are valid even if the denominator has a exponential term. So, and you will see that the computations are easily possible even with the denominator having exponential terms, but the theory also holds for time delay systems is something that we are not going to prove, but we are going to just state that, and then that way we kind of complete the whole sequence of ideas. Okay, so, in the last lecture I mentioned this. I said if you had a function x and f of x, basically if we translated this to s and f of s, remember I said this itself is a complex variable and this also is a complex variable. So, I cannot just do it in this 2 axis. So, I need one separate plane for s and another plane for f of s. Okay. So, this is something that we saw in the last class, and then we also saw that if f of s is some, let us write this in this form, some k times s minus z1 all the way up to sz minus zm divided by s minus p1 all the way up to s minus pn. We said that the zeros and poles of this transfer function will have to be plotted in the s plane, because what you plot in the f of s plane is actually the value of f of s when s takes some particular argument. However, if you want to plot the zeros and poles of this transfer function itself, you do not plot them in f of s, you plot them in s plane. So, you might have zeros here, poles here and so on. Okay. So, that is something that you have to remember. So, this distinction you have to remember. Now, what we are going to do is we are going to look at some interesting ideas when we think about this s and f plane. So, let us assume that I have some f of s. Okay. So, I am not even going to write this in the pole 0 form yet, but I am going to show you something called contour mapping, and then we will pick up on this idea and then see how this is useful from a stability analysis point of view. Okay. So, let us start with the s plane. Okay. So, these are the set of values that s can take, and here is an fs plane. Okay. So, let us look at this. Now, what we are going to do is something interesting. So, what we are going to say is, okay, let us look at this s plane. Okay. And I will draw something here and explain what I am doing here presently. So, let us say this is j, which is 1 times j at 0, this is let us say 2 j, let us say this point is 1 plus j, and let us say this point is 1 plus 2 j. So, you can see this. So, this is the real axis. So, this is the imaginary axis. So, when I go y axis here, then if I take a single unit, that is simply j, 2 units will be 2j, and I do this here, this is 1. So, this point will be 1 plus j, this point will be 1 plus 2j. Now, what we are going to do is the following, and you will see why we do this when you finally bring all of this together. Right now, what we are going to do is, let us say I start a contour here, and then I start from this point, and then I go along this line, and then let us say I go along this line, I go along this line, and I come back to this line. Okay. So, this is what I am going to call as a closed contour, which starts from here, goes around, and then comes back to the same place. So, this is a closed contour, and the other thing that I want you to notice about this closed contour is this closed contour is also moving in the clockwise direction. So, basically I have moving in this clockwise direction. So, let me pick a contour like this in the S plane, and I want to know, as I move along this contour, for every point on this contour I can get a value for f of s, because this is in the S plane. So, if I take any point here, S will take a particular value, I can substitute this into this and then see what the value f of s will take. Okay. So, what I want to do is take a closed contour on the S plane and then see what will happen in terms of the f of s plane. So, when I say I want to see what will happen in terms of f of s plane, what I am saying is every point on this contour, if I compute an f of s and plot it here, how will that look? Now, since the beginning and the starting point are the same, I would expect this f of s contour also to be a closed contour, but the shape of that will depend on what f of s is. So, let us do this exercise to quickly understand how this works. So, if let us take some f of s and then understand what happens. Let us say if f of s is actually something like s plus 2 for example, then this point here where s equal to j, if I substitute into this, then f of s equal to j plus 2 when s equal to j. Okay. So, when I take s equal to j, I get j plus 2. So, that means this is, let us say 1, this is 2, this is 1, let us say this is 2. So, j plus 2 will be mapped to this point here. So, basically you will have this point mapping to this point. Now, if you take this 2j, so f of s is going to be equal to 2j plus 2 when s equal to 2j. So, that point is going to be basically this. Okay. So, this point is going to map onto this. Now, if you take this point, s is 1 plus 2j. So, f of s will be 1 plus 2j plus 2, which will be equal to 3 plus 2j if s equal to 1 plus 2j. So, this point basically will be 3 plus 2j. So, this point will map onto this point, and you can also see that this point will map on to this point. Okay. So, the 4 edge points I have shown you how they map on to different points on the f of s plane, and any other point here also will be translated likewise. So, basically this will just be a translation by 2 units in the real axis of this contour. So, this S contour will turn out to be the following contour here in f of s plane. So, this is very simple idea of how this goes. So, any point here will also be plus 2 here. So, simply you move it in real axis by 2. Okay. So, this is a very simple idea. So, basically what we have done is we have mapped a contour in the S plane to another contour in the f of s plane. The procedure is very simple. I take different points in the S plane and then compute the corresponding f of s value and simply plot those in the f of s plane, and this is very simple function f of s. Okay. Now, let us do slightly more complicated function. We will keep the S plane to be the same, okay, and we will keep the contour in the S plane also to be the same, but we will change f of s and then see what happens to the contour in f of s. Okay. So, the contour that you see in f of s really depends on what f of s is. So, let us just do a simple change. Okay. So, now let us assume that I have an f of s which is 1 by s plus 2. not s plus 2, 1 by s plus 2. So, if you want to think about this, this is like a 0 at minus 2, this is a pole at minus 2. Now, let us see what will happen to the f of s plane. Okay. So, now when I put j, okay, so f of s is 1 by j plus 2 when s equal to j. Now, when you have this j plus 2 from simple complex variables, what you can do is you can multiply this by 2 minus j in the numerator and denominator. So, this will be equal to 2 minus j divided by 2 plus j into 2 minus j will be 2 squared minus j squared. 2 squared is 4, j squared is minus 1. So, 2 squared minus j squared will be 5. So, you will get 2 by 5 minus 1 by 5 j. So, this point now becomes the following. So, if I take this as minus 1 by 5 and slightly more, this as 2 by 5. So, this point is this. So, this point now you notice changes to this point right here. So, you can see the difference, right, and then similarly let us just do another point 2 j. So, if I put 2 j here, so f of s will be 1 by 2 j plus 2. Now, if I multiply both sides by 2 minus 2 j, what I will get is 2 minus 2 j divided by 2 squared minus of 2 j squared. 2 squared is 4, 2 j squared will be 4 times j squared is minus 1. So, this will be 4 plus 4, so this will be 8. So, I will get 2 by 8 minus 2 j by 8. So, 1 by 4 minus 1 by 4 j. Okay. So, that is another point that you can put here and so on. So, similarly you can compute for this point, you can compute for this point, and you can compute for any intermediate point, and then you will get a closed contour in the f of s plane. Now, notice that this is simple translation, just the minute I made this into 1 over s plus 2, it is little more complicated in terms of the contour change, or contour has changed completely in this case. However, the concept is very simple and the same. So, for every point in s, you compute a corresponding f of s based on whatever is f of s, and you will map a closed contour in the s plane to a closed contour in f of s plane. Okay. So, this is the first basic idea that we want to understand. So, you might ask, okay, this is good, so we can do this, but how is it useful for us, which is what we will see in the next few slides. So, the key idea that is going to be very useful for us is the following. So, we have still not come yet how we are going to connect this to control. We are still looking at polynomials and looking at contours. So, the first question that is going to be answered in terms of how is this useful for even polynomial by polynomial, we are going to look at this main result here. Okay. So, let us again do this. So, let us say I am looking at some f of s, okay, and this is a numerator by denominator polynomial. Let us assume we have written this in this form, k times s minus z1 all the way up to s minus zm divided by s minus p1 all the way up to s minus pn. Okay. So, there are m zeros and n poles for this. So, these are just illustrations. Okay. So, this plot is to give you an idea of the main result that we are going to talk about. So, again just like we had in the last slide, we are going to have two planes. So, already notice that one graph which we used to understand x and a function of x has become two planes to understand s and a function of s, where s is a complex variable. Okay. So, this is an s plane and this is f of s plane. Okay. So, we have not even kind of said what this f of s exactly is, but I am going to make some points based on this pictures. Okay. Now, take a system here where I have, let us say, 2 poles and 3 zeros. The red circles are the poles and the blue circles are the zeros. Okay. So, for this function obviously I am going to plot the poles and zeros in the s plane. So, this is something that we have talked several times. Okay. So, we plot the zeros and poles on the s plane, and let us say for this function we have these 2 poles and 3 zeros. Now, what I am going to do is I am going to take a contour. Let us say I start a contour, let us say here, and basically I keep moving in the clockwise direction. in this contour. Okay. So, I start here and I move in the clockwise direction, let us say, and I come back here. So, that is one encirclement or one full contour, one full closed contour. So, I start at the same point and I come back to the same point in a clockwise direction. Now, let us say, just like how I showed you in the last picture, I were to look at what happens to the f of s plane contour. Okay. So, f of s is going to be some function and it is going to have these zeros and poles, and I want to see what happens to the f of s plane. So, let us say we start at some point, because it is going to be a closed contour, we do not have to worry about where we start. So, wherever we start we will come back to this same place. So, one place to start might be here. Okay. So, I go here and then I start. So, it is going to be a closed contour. So, I start like this, sorry. So, you see this going in this direction, I should. So, you have to follow the direction. So, I follow this direction. Okay. So, I go like this. Okay. And for the full contour it is not done yet. So, I continue like this and then I come back to the same point. Okay. So, this is what I do. So, basically what this shows is, this is done actually for a particular function. The computations we are not showing, I am just showing you the results that you get. So, when I start with an S plane and I basically have to complete the whole closed contour, and as I complete the closed contour on the S plane, I have gone through a contour like this. Okay. So, contour something like this. Now, I will just mark the origin here. So, the origin is here inside the contour. Okay. So, the main result is the following, and before I say what the main result is, if we were to count the number of times we circle around the origin in this case. So, if I start here and then I go like this, so this is the origin. So, I am circling around the origin, and when I come back here I have done one full circle. So, imagine that this is not there, the inner contour. If you look at this, then you will notice that you have done one full circle around the origin. However, notice the direction of the circling, the direction is in the anti-clockwise direction, though in the S plane we went in the clockwise direction, in the FS plane we are going in the anti-clockwise direction. So, I have done one circle, but by the time I have done one circle, this closed contour is not finished yet. I still am going around this closed contour in the clockwise direction. So, I am here, so it still continues. Now, I go around and come back here. Now, forget the outer circle, from here to here I continue to circle and origin is inside. You will see I have made another circle again in the anti-clockwise direction around the origin. So, basically when I convert this contour, which is the clockwise contour in the S plane, to an FS plane, in this case I seem to have made two counterclockwise encirclements of the origin. So, that is a word that is used. So, encirclement means, if you look at this, there is one encirclement here and another encirclement here, and I have now two encirclements around this origin. Okay. So, let us look at the next picture and the third picture, and then I will tell you the main result, which is a very interesting result that comes out. Let us say we have another f of s where I have, let us say, two zeros and one pole. Now, let us say I start here much like before, and then I go one clockwise loop around this and I come back to this same point, and then I say how does this one look in this. So, now again in the FS plane I can start at some point, and then when I finish here I should also finish here and see where I end up. So, let us say I start at this point and then I follow this. Now, again I am following this contour, okay, and then I come here. Okay. So, this is the first contour, still this is not finished. So, as I go move along, there is more to do here, that is what these plots show. Now, if you again look at this now, just the outer, you will see origin is here, you will see I have encircled origin once, but now in the clockwise direction, okay, and I am not done yet. I have to then still continue around here and come back and stop here. This is when this whole thing has come back to whatever its initial location. Now, if you notice, after making one encirclement, I come back again and make another encirclement of origin, and that is also in clockwise direction. So, if you were to look at all these encirclements, and that is where these arrows are given. So, this is 2 encirclements, however, it is in anti-clockwise direction. Here I have 2 encirclements in clockwise direction. Okay. Let me take a third example and then see this, and then we will bring all of this together in terms of the major result. Okay. So, now it is another f of s. This time I have 1 pole and 2 zeros, and let us say I do the same clockwise encirclement in the s plane, and I want to look at what happens in the f of s plane. Now, the difference is that in this plot I had only poles inside the encirclement. When I say inside, it is inside the closed contour. There are zeros for the transfer function, but they are outside the contour. If you look at this picture here, I have 2 zeros inside the closed contour and the pole is outside. That is how I have chosen the contour. You can choose to encircle everything also, it does not matter, but I am just saying what we have done. In this case, we have encircled in such a way that all the zeros and poles are within the closed contour, and keep in mind every time we are doing this movement in clockwise direction. So, this movement we are doing in clockwise direction. So, in this case, let me again trace this. So, maybe I start here and then I go, and now you see I am moving in the clockwise direction, and then I do this, I come back here and I am done. Okay. So, when I finish this contour, this is what the picture says, you are done. And now again let us plot the origin is inside. Now, if you notice this, starting here I go clockwise and I have made only one encirclement of the origin in a clockwise direction. So, one clockwise encirclement. Okay. So, now you might ask, why is it sometimes in the f of s plane I have one encirclement, sometimes I have 2 encirclements, sometimes in the clockwise direction, sometimes in the anti-clockwise direction, while I am always having my contours in the s plane in a clockwise direction. Okay. So, the result that puts all of this together in a single statement which handles all of these cases is the following. So, this is the simple mathematical statement n equal to z minus p. Okay. So, let us expand on each of this. N is the number of clockwise encirclements of the origin in the f of s plane. So, that is what we actually find ultimately. So, in this case n is minus 2, because the number of clockwise encirclements in this case would be minus 2, because I have 2 encirclements in anti-clockwise direction. So, whenever it is an anti-clockwise encirclement, we use a minus. Okay. And if you take this case, this will be 2 clockwise direction. So, n will be 2. In this case, if you take this is 1 clockwise encirclement. So, n will be 1. So, this result, what will happen in the f of s plane? Will you have 2 anti-clockwise, 2 clockwise, 1 clockwise, 1 anti-clockwise and so on, can be specified actually without plotting this at all. That is the beauty of this result, right. So, right now I am going to show you that you could have simply mathematically said how many encirclements will be there, and will these encirclements be in the clockwise or anti-clockwise direction, by just looking at the contour in the s plane and what is inside the contour in the s plane. So, that is the important thing. So, if you take this f of s for example, and you went for this contour, if you notice within the contour, inside the contour there are 2 poles. So, the number of poles inside the contour in this case is 2. Though the f of s itself has 3 zeros, the way we have chosen the contour, we have excluded all the zeros here. So, the number of zeros in the f of s plane, sorry, this is the number of zeros inside the contour. Is 0 in this case, because while f of s itself has zeros, inside the contour we do not have any 0. Okay. So, this is 0 minus 2, and you will get this number as minus 2. So, n equals 0 minus 2 minus 2. So, that is 2 anti-clockwise encirclements. Now, if you look at this f of s, though this f of s has 2 zeros and a pole, we have excluded the pole and we have done a clockwise encirclement only around zeros. So, in this case, for the second case, n will be 2 zeros inside the contour, no poles inside the contour. So, 2 minus 0 is 2. So, I have 2 clockwise encirclements. Now, in the third case, if you look at it, I am mixing both zeros and poles. Now let us see whether we get the correct result. In this case, n equal to 2 zeros inside the contour and 1 pole inside the contour. So this is 1, so plus 1, this is 1 clockwise encirclement. So this is 2 clockwise encirclements, this is 1 clockwise encirclement, and this minus 2 case here I have 0 minus 2 will be 2 anticlockwise encirclements. So interestingly, you could have predicted how many encirclements around the origin will be there by simply looking at how many poles and zeros are captured within the contour. So for example, if for the same f of s I had not done this contour, but let us say if I had done a contour like this, okay. So I go like this, which is clockwise for this, and then ask how many encirclements will be there in f of s plane. You do not have to actually plot this, now you can say what it will be. So if you look at this contour and what is inside the contour, there are 3 zeros and 2 poles inside the contour. So n is equal to 3 minus 2 will be 1, so you will have only 1 clockwise encirclement here. Now if let us say my contour was something like this instead, then I have 2 poles and a 0 inside this contour. So the number of encirclements for this contour when I plot them in f of s plane will be 1, number of zeros is 1, minus 2 number of poles inside the contour. So 1 minus 2 is minus 1, there will be 1 anticlockwise encirclement. Similarly, you can make arguments for each of these other f of s and the plot. So even for the same f of s, when I look at the contour in the f of s plane, that depends on what is the contour in the s plane, and all you need to do is you have to look inside this contour and then see how many zeros and poles of f of s are inside the contour, and when you plot this closed contour in f of s plane, then the number of clockwise encirclements is simply going to be z minus p. So this is the key result that we have. Okay, so with this idea of contour mapping s plane and f of s plane and so on, hopefully you have an idea of these pictures. Why this happens is something that I have not said, and I am not going to say it because that would require a lot more complex variable analysis, which is not really required at this time for an undergrad control. All you need to know is how you interpret this, get the basic ideas as to why there is an s plane and an f of s plane, and how you can actually guess how many encirclements will be there in the f of s plane based on the contour that we choose in the s plane. So these are important ideas that you have to understand. Basically, if you understand this picture and you are able to basically understand clockwise, anticlockwise encirclements, inside, outside contour, zeros and poles, why do we plot zeros and poles in the s plane, and look at contours in the f of s plane and so on, that is good enough. Okay. So now that we have seen all of this, the next question that naturally arises is that this is all good, how is it useful for control? Okay. So this is what we are going to see, and once show you how it is useful for control, then of course the next question is how are we going to use this for time delay systems. Okay. So when it comes to the control system, the way we are going to use this is the following. So we typically let us say have a closed loop control transfer function, and we are looking at the stability of the closed loop control transfer function. So basically we are looking at let us say GC by 1 plus GC. This is something that you have seen many times. So this is going to be some numerator by denominator form, and if I have time delay elements in my controller which basically gets introduced because of time delay in my system, then what is going to happen is this denominator polynomial is going to have infinite number of poles, because if I conceptually expand e power minus tau ds into an infinite polynomial, I will get lot more poles. So that was our problem. Okay. So how do you guarantee that none of the poles actually clip into right half plane is what we are interested in. So basically if you think about an S plane for this, so this is basically what we are going to say is f of s, right, and this is itself is a transfer function with s. So if I want to know if this system is stable, then what I can do is I can just take this 1 plus gc. Okay. Why am I taking 1 plus gc? Because when I write this in a numerator by denominator form, the zeros of 1 plus gc will become the poles of this. Okay. So if I for example write this 1 plus gc itself as some numerator by denominator form. Okay. Now gc itself you can write, let us say, by some let me call this some numerator by denominator form. So when I do gc by 1 plus gc, I will get a numerator by denominator divided by numerator by denominator. But you will notice the way this is written, the denominator of 1 plus gc will be the same as the denominator of gc. So this and this will get cancelled. So you will have some numerator of gc by this numerator of 1 plus gc is what will be the final expression for gc by 1 plus gc. So again let me explain. If I write this as ns by ds and gc as n1s by d1s, because we are going to take these denominator polynomial, multiply by this and then divide by the same denominator polynomial, the denominator polynomial of gc and 1 plus gc are going to be the same. So they are going to get cancelled. So this whole transfer function is going to be the numerator of gc divided by the numerator of 1 plus gc. So if you look at this as this, then the stability of this gc by 1 plus gc depends on the numerator polynomial of 1 plus gc, and in fact when you think about this numerator polynomial of 1 plus gc, we are looking at the zeros for 1 plus gc, because if this is numerator polynomial of 1 plus gc, these will be the zeros of 1 plus gc and this will give you the poles of 1 plus gc. So basically what we are saying is, I want to find out if this numerator polynomial of 1 plus gc has any zeros in the right half plane, right. If the numerator polynomial has any zero in the right half plane, then the closed loop system is unstable. So this is an important idea. Please work this out for yourself and convince yourself that this is the way to look at this, because this is going to be something that we will keep looking at again and again. So basically what we can do is, ultimately because we are looking at numerator of 1 plus gc, we are looking at 1 plus gc itself. We are forgetting gc because we have now established that the numerator of 1 plus gc is important, or in other words this 1 plus gc will be some numerator by denominator polynomial, and if I say this is f of s, then basically I want to know if this f of s has any zeros in the right half plane. Okay. So the whole question of stability of the closed loop has boiled down to this, where I am saying f of s is 1 plus gc, which I can write as a numerator by denominator polynomial. Now from this I know if the zeros of this f of s, which is 1 plus gc, which is the roots of the numerator polynomial, are in the right half plane, then I am going to have my closed loop system becoming unstable. So the question is, how do I connect what I want to solve here with whatever I have seen till now? So till now what I have seen is, in the S plane, if I take a contour, right, if I take a contour in the S plane without actually computing the poles and zeros inside the contour, I can always find out how many poles and zeros are inside the contour, not exactly the number of poles and zeros, but a difference. Okay. So remember the last time we had n equal to z minus p. So in the S plane, if I take any contour, okay, and I know the f of s form 1 plus gc, if I were to just take each point here in S plane and then I generate a corresponding f of s whatever contour that is. Okay. So I go from S to f of s. Remember this, you do not need to know the zeros and poles, because it does not even have to be in the root resolve form, because I have a polynomial, numerator polynomial, I have a denominator polynomial. Conceptually what I am doing is I am taking every point here and then I am finding a corresponding f of s, right, and simply substituting it. So once I find the corresponding f of s, I will get a contour here. Okay. So it can be just a polynomial form, not even root resolve form. Now without resolving for roots, without finding the roots, what I can tell you is within this contour for this f of s, what number of poles and zeros are there in terms of a difference. So I can tell you the z minus p. So how many zeros minus poles are there inside the contour. So this I can do without resolving this into root resolve form, without actually computing the poles and zeros, because once I get this form, every point here can be translated to a point here by simply substituting this s value into this f of s. So that is the key idea. Okay, so this is something that you should understand. Now essentially what is the contour now I should take in the S plane to look at the stability of this GC by 1 plus GC. So ultimately what I want to show is the whole right half plane has no zeros, right. So if for 1 plus GC, if the whole right half plane has no zeros for 1 plus GC, then there are no right half planes poles for GC by 1 plus GC. So basically the contour I have to take in the S plane is the whole right half plane, and the way you conceptually do it is you start at minus j infinity here, and then you keep going. Okay, this is in the clockwise direction. So this is minus j infinity somewhere here. Okay, and you keep going in the clockwise direction up to j infinity, and then you take a big arc around here and come back here. So this is what is plotted here. Okay, so if you make this radius infinity, then basically what you are saying is I am going to cover the whole right half plane. So this is right half plane and this is the left half plane. So basically I start from minus j infinity, go all the way up to j infinity and take a very large infinite circle and come back to minus j infinity. Now if I take this whole contour basically covers all of RHP. Now if I plot a corresponding Nyquist plot, or I plot this in the Fs plane, as I move here what happens to f of s, then depending on how many encirclements of the origin I see in the f of s plane, I will be able to say how many z minus p's are there within this contour. Okay, and remember, because I am looking at 1 plus GC, I am interested in the number of z's, because the zeros of 1 plus GC will become the poles of the closed loop transfer function. Okay, I cannot separately get z and p, so we will solve that problem again. So we will go one by one. So first, from the Nyquist diagram, I just want to explain how we convert that to a control concept. So we will still see how to get rid of this z minus p problem, but let us assume that I can find out how many zeros and poles are there within this contour. At least we have got the quantity of interest, the number of zeros of 1 plus GC into this picture already. Okay. So if I can plot this, then by looking at just that plot, whatever it might look like this or something else, I can actually tell you how many z minus p, what is the value for z minus p. That is just simply given by looking at this encirclements of origin. So if it encircles origin once in clockwise direction, then we will say z minus p is 1. If it encircles origin once in anti-clockwise direction, we will say z minus p is minus 1 and so on. Okay. So that is how this notion of Nyquist diagram, Nyquist plot is converted into a control idea. So that is a conversion from whatever we saw in the previous slide to a control idea, and the key insight is we know how to characterize how many zeros and poles are there in terms of a difference z minus p inside a closed contour by looking at number of encirclements around the origin in the f of s contour, and this contour computation is very simple, whatever be the f of s. So f of s can be some a naught plus a1 s all the way up to am s power m divided by b naught plus b1 s all the way up to bn s power n. So I do not even have to have this in root resolve form. It could have for example just to make sure that we understand this, it could have some other time delay term here also, it does not matter. So as long as I have this f of s, for every point on this contour I can substitute the s value into this, remember, and simply compute an f of s. Okay, it need not, I don't know the roots of this polynomial. Clearly there are infinite number of roots for this polynomial. All I am going to do is I am going to take an s value and simply plug this in to this f of s, and I will get a corresponding point here. So conceptually, if I am able to take all of these points and then compute this and plot this f of s diagram here, then I am done. now I can actually look at the encirclements of this around origin and then find out how many zeros and poles are there in terms of a difference. Okay. So, this is the key idea that translates whatever we have learned till now into a control concept. Now, we will see how to take this forward in terms of a clear result on stability for closed loop control systems in the next lecture. Thank you.